So we do have a code of conduct link to the top of our session. There's also an attendance sign in the Google Doc link to the session in Kiko Chat. So please do add your name and affiliation there. We'd love to follow up afterwards. You can see our agenda right below that. And I think that's a good kind of place to start. So we're going to start off with a quick 5-minute silent exercise, and then we're going to get into our speaker talks. Each speaker is going to have about 6 minutes with a couple minutes of questions afterwards, and then we're going to do some collaborative work and breakouts, and eventually I'll come back together. So to start off, I'd like to have you all navigate within the Google Doc under the agenda. Where'd our 10 urgent challenges go, Jensen? We did have them there.
I see 10 urgent challenges.
You do?
The title.
Oh, we used to have 10 urgent challenges listed 1 to 10. Somehow they went away. We've solved everything. There's no challenges. All right, Jensen's gonna put our 10 urgent challenges in there. And he kindly came up with 10, there they are, 10 urgent challenges that he'll also reiterate at the end of his talk. But he kind of sees these as 10 urgent challenges within this space. And what I would like this crew to do, and as soon as he's done kind of dealing with text formatting, is if you could look at those, and even these might not be your 10 urgent challenges, but I guarantee there's a couple that ring true to you in the space of AI ML. So if you could take a look at them and +1 your top 3. So go ahead and just add a +1 to the 3 out of the 10 that I'm going to change this print, that you see as your kind of top 3 challenges. So I'm just going to give everyone 2 minutes to work through this.
And at the end of 5 minutes, somebody need to do the math with us.
Good reminder, Yuhan. And it looks like we have 9 listed. Jensen, did we have one that dropped off? No one is surprised that
we
number
actually
2 is getting a lot of +1s. Go ahead, Jensen.
We only have 9. I think I missed one from the beginning, so it's fine.
For those of you that may have been just joining, we're in the Google Doc and we have a list of urgent challenges, and we're asking everyone to add a +1 to what you think are your top 3, your personal top 3. I'll just give 1 more minute for people to add that.
Annie, I think I see a raised hand.
Say that again?
I see a raised hand. Somebody has raised their hand on Zoom.
Oh, a raised hand. Yeah, Tom?
I just wanted to ask about number 9, provenance. Is that provenance of the model or provenance of the data that trained the model, or all of the above?
It's all of the above.
Okay.
The provenance for to produce the same results in the future, and that information can all be counted as provenance in machine learning.
Okay, thank you.
Yeah, no problem.
All right. I like how in training data preparation, a +1 has turned into a +11, but I'm just going to assume that's 11 additional people saying that that's a +1 for them. So I think no big surprises here in terms of what the group, we were initially going to have people write down what their top 3 challenges and we knew this training data would come up. So we figured we'd just put it out there and let us focus or think about a couple others as well. So, so keep adding those +1s. And if anyone has any additional thoughts about that, or you want to add your own urgent challenges that we don't have on this list, please go ahead and add those and add some notes there if people have thoughts while we're starting off with our talks. So with that, Jensen, I will kick it over to you to introduce our first set of 3 speakers.
Thank you, Annie. Our first speaker is Mostafa from Stanford University, and his talk is going to be about AI in earthquake. Mostafa, you can go ahead.
Sure. So could you see my
Yes.
PowerPoint?
Yep, and just a reminder for everyone else to mute while Mustafa is speaking. We appreciate it. Thank you.
Okay. Hello, everyone. This is Mostafa Musavi. Thank you for having me. I'm going to talk about how AI can change the way we monitor earthquakes in these modern days. So this is the map of earthquakes with magnitude equal and greater than 4 that happen over 1 year time period. These are the earthquakes that were large enough to be felt by most people in the affected areas. There are almost 11,000 of them in this map, and these are enough to give us some insight about very large scale processes in the earth, like these active boundaries of tectonic plates. However, there were almost 1 million earthquakes with magnitude 2 and 50 million magnitude 1 earthquakes that happened during the same time period, but they were missing from our previous map that I just showed you. These smaller earthquakes are those that don't get felt by people, but they do get captured by our seismic sensors, and they can provide some useful information as well. The reason that they normally don't show up in our earthquake catalog is mainly because the traditional algorithms that are commonly used by earthquake monitoring agencies are not sensitive and robust enough to fully process all these smaller signals. Moreover, traditional techniques are not either efficient enough to keep up with the growing volume of the seismic data that we are recording by either these cheaper seismic sensor or unconventional methods like these ones that are getting very popular these days. So to extract the valuable information from these high dimensional, large volume data sets and gaining new insights about physical processes in the earth, we need new tools and algorithms. And this is why in past few years, we have been working on developing new machine learning based model for this, because this is because we think this is where AI can play a key role. We develop a deep learning model that can receive a noisy waveform like this one and decompose it into earthquake and non-earthquake signals. This can help detecting the earthquake using another model that we developed to identify earthquake signals based on their time frequency content. We built a sophisticated model that can pick P and S wave arrival times and that are needed to locate an earthquake. We built a deep learning approach to determine the polarity of first motion and also discriminate the local and teleseismic events from each other in an unsupervised fashion. We showed that machine learning can be used for a fast estimation of earthquakes magnitude. We developed a Bayesian deep learning approach to estimate the location of these smaller earthquakes based on waveform recorded on only one single station. And to build all of these models and also promote the machine learning research in seismology, we put together a large-scale, high-quality labeled datasets of earthquake signals and made it publicly available to everyone. With the help of these new AI-based model, now we are able to detect and characterize many smaller earthquakes in much less computational time. And by improving our ability to detect and locate these smaller earthquakes, we can now build a very high resolution image of fault structure and get a better view of how the earthquakes interact with each other, how they spread along the fault, how they get started, and even how they stop. This is one example for a sequence of earthquake that we just studied in Japan. You see that a structure of seismogenic part of the fault very clearly from this pattern of macro earthquake to parallel fault are clearly observable in this cross-section view. So in summary, AI can help us to process seismic data not only more effectively, but also more efficiently and precisely as well. And as a result, we can extract new information and insights from the same data and instrumentation configuration. And of course, there are still a lot of room for improvement, but we think that AI can ultimately open some new doors in seismology by providing us these tools that would enable us to process the data volumes that we have never processed before with the precision that we never had before. And this is a very exciting time for observational seismologists like me, because we don't know that how much new things we can learn about the Earth and its little quirks when we look at it at this scale and with this resolution, using these unprecedented data and techniques that we never been exposed to. So that was my last slide. Most of these models and data set that I just talked about in this presentation are publicly available from this GitHub page. More than some of these models, like the earthquake detection model, has been used in more than 40 countries so far. And the results were very promising. They have been working very well in different settings and different geographic location. So I stop here and would be happy to take any question.
Thank you, Mustafa. That was amazing. Way to go, Stanford Geophysics. I asked if that was a KML file you had of earthquakes with all the kind of magenta triangles. That would be a great data set to cruise around. But I did want to hand it over to Jensen for moderating the Q&A. So Jensen, are you there?
Yes, very fantastic work. And there is several questions. I think the first one from Ryan. Is this model ready to be deployed? And what was your process to make it usable?
Oh, some of these works that I've been showing you, like the works that have been done for earthquake detection and phase peaking, that are main like processes that we need to locate the earthquakes. These are completely ready to use. We wrote the package in a very user-friendly fashion, so they can be installed and off the shelf be used just by like writing one comment line in the terminator. But some of the others one, like the works that we are doing on magnitude estimation and location, for instance, these are still in like experimental phase. So we are exploring like different like configuration of models that they are not like this pipeline is not fully ready, but the first part, which is like the main part of like finding all these little earthquake and the arrival times that can be used with the conventional techniques for, sorry, I forgot to stop sharing. That can be used with these like conventional algorithms to do the rest of the work and locate all these earthquake. They are ready to use, and as I said, they are publicly available from that GitHub page.
Great. I think we don't have time for another question, so let's go ahead, and Mustafa, probably it's better if you can respond in the chat box.
Sure.
Great, wonderful. So our next speaker is Aji from University of Washington on AI in snow mapping. Aji, take it away. Aji, are you there?
Yes, yeah, I'm trying to share. 1 second.
Great.
Okay. Hope you folks can see the first screen.
We're seeing in presenter mode. Do you want to see if you can switch it over to full screen?
Okay, 1 second. Okay, is this better?
That looks better.
Okay, sorry about that.
No
Okay, hello folks. I'm Ajay John. I'm a graduate student in biology. I'm working with Tony and Canestra and Nicoletta. And we are interested in applying AI-based techniques to understand snow. Here the focus is montane ecosystems, but primarily we are interested in forests and meadows as well. So our primary motivation, and this is the primary motive of rather mine as well, is to understand how in the montane ecosystems, snow, which plays a predominant role from flowering of the species to how it's, so the onset of flowering to how it triggers the pollination events. So any delay in snow melt could have repercussions downstream. It doesn't stop it there. We know that, apart from ecological questions, it is quite relevant. The estimation of snow water equivalent and snow products are very important in the water resource planning, in forest management as well. So, and just to give you an idea, means where are we going with it, is that in terms of artificial intelligence, it has played a pivotal role in processing large data sets. And I think I saw that in one of the top 10 items is that, how do you do the data wrangling, training, and all of it? But it's a good time because now we can. So I have shown a couple of this image here where we show the grid size, where we get remote sensed imagery, and the sampling frequency. And we are interested in how to use the fine scale resolution. And I put in planet with the red dot over here, and that gives us the idea of a fine spatiotemporal resolution, which would mean the 3-meter resolution or 1 to 3 meter resolution. And we get multiple acquisitions within a week. Now, I want to give you a quick preview of what folks had done by Tony and all, where they were one of the first ones to show this approach where using a fine resolution imagery can we produce sort of a daily product where we could tell, the snow in forested areas, non-forested areas, and pretty much on like, actually I should say big classification would be that in no canopy cover to actually having a canopy cover. And so this is showing how the planet RGB image, this is a 3-meter image, and how the LiDAR, which is an ASO observation mask, which we can produce, which on thresholding 10 centimeter above, and how the convolutional neural network prediction comes with not accurate, but it is close to being a good model. This work is in review, but it was the first one to show that yes, the CNN-based model, it is transferable because the folks trained in Tuolumne Meadows in California, and we're able to apply in Colorado. Now, it did well, except that we saw that it didn't perform that well in the forested areas. So I got interested in it, and that's where we took it forward to see how can we improve this model, and this machine learning model, which is a convolutional neural network underneath, can be improved to work in the forested sites. And this is a very high level showing you the sort of the workflow where we take the ASO snow observations as the ground truth, and then we couple that with the plant imagery, which gives us a fine resolution spectral bands, visible and infrared, and then we use that information to feed it to the neural network, and then we use an algorithm called CNN algorithm called UNet, which has been very promising in the biomedical field, and this was adapted, and it worked quite well. And so before we went into how we could enhance it, we said, okay, how could we improve it? So when we looked at what other folks had done, they said, okay, to improve the model in forested areas, you could look at the vegetation, for example. You could give a proxy of vegetation like a leaf area index, or something to which gives an idea of the canopy. Or you could add some, for example, NBD there's a band ratio, like normalized band ratio. Or we could give some idea of the slopes, where the intuition is that where different topographical features would affect the distribution of snow. Or rather other works where DEM-based attributes like the slope and elevation and northness. So the idea was, okay, we could try that, where we could add these layers to those bands and actually train a model again. So we did a minor enhancement to the same model, where we start stacking these images, stacking these sort of layers, so as an input layer to the training, with layers of DEM, slope, and other attributes. So similarly. And we used the same system where we trained it on the upper Tuolumne and tested or validated, trained and validated in Gunnison, and trained and validated in upper Tuolumne, and tested in Gunnison. So, and our preliminary results show in terms of the stacking, we saw that if you add the spectral bands to this DEM and slope and aspect and northness, that seems to be more explaining the variation or the distribution of snow in the forest understories. And we tried various other models, and this is showing you that which ones we found like least relevant to most relevant. So the NDVI here is the least. We tested on the Gunnison. These were the metrics we got, where the F score was better than what the original paper had done in Gunnison, but we wanted to go more deeper into it. So we looked at how our prediction turned out in the Gunnison compared to the LiDAR, which is the ground truth we're using. And we saw that it did well, but it could still be improved. So here on the left-hand side, you can see that that's what the ASO thresholding we used of a 10 centimeter. And then how on the right, where the prediction happened, we still see that we are sort of underestimating the snow in the forested areas. This is just showing a sample of a particular area in that, where we see that how the model seemed to be predicting quite well with the optical imagery which we get from the planet, but it's still not able to capture the granularity. So big picture in terms of the next steps, it works well. It's a good improvement, but we still want to have a quantifiable measure. And I think one of the items which I saw the top 10 was that how to explain these with respect to canopy metrics. Can we use a canopy density metrics of how dense it is, and then explain how the model is performing, and test at a totally different site at Swiss site where we have rather data for, or adding like multiple captures of the imagery. So one in, let's say, in spring, and one beginning of summer, or one in winter and spring, and then train it. Or then combine the California and Colorado data sets for training, and then test it in Swiss sites. That's it. Thank you.
Thank you, Ajay. There's one question, actually my question. How does the shadow, so is the shadow affecting the performance of the neural network?
Yes, it is. And actually, that's one of the things I didn't highlight, but we do have minor issues with the clouds and shadows. And that does go away in some of the models, like when we used NDVI as one of the layer, that seemed to be handling the shadow and the clouds quite well. But in the DEM-based model, that was still a problem.
Mm-hmm.
So we don't have a solution quite yet. We're thinking that we might add NDVI, but we haven't tried it yet. Good question.
Thanks. Okay, so let's move on to the next speaker, Mike from Africa Air. Cindy, you play his video?
Hello, my name is Mike Giordano, and today I'll be talking about low-cost air quality monitoring and machine learning, perspective challenges and lessons learned from the Africa Network. So I will preface this by saying that most of the data that I will show here is not actually from Africa, but
all right. Okay, sorry. I'm trying to turn up the volume.
For reasons that I'll explain in a second. So I want to mention Africa Air here, which itself is a global consortium of researchers interested in building capacity.
I'm gonna just restart everything. Is that fine?
Yeah, and it's not too bad. We could hear the audio. I mean, it was a little soft, but not.
Yeah, we don't have to restart from the beginning. Just
yeah, I think it's okay.
Perspective challenges and lessons learned from the Africa Network. So I will preface this by saying that most of the data that I will show here is not actually from Africa, but low-cost sensors may be the most impactful in places like the Global South, for reasons that I'll explain in a second. So I want to mention Africa Air here, which itself is a global consortium of researchers interested in building capacity for air quality monitoring in Africa. The work I'm talking about here is being actively applied to our sensors in Africa. And so I encourage you to check out our website and our Twitter. I won't spend a whole lot of time on this. I think most everyone knows that poor air quality has deleterious effects on health and climate. What I will say is that while we don't have much monitoring in Africa, the estimates that we do have suggest that most of the population of Africa are chronically exposed to poor air quality levels. I mentioned that we don't have a lot of monitoring in Africa, and this is because traditionally, air pollutant monitoring has been done with reference grade monitors that are highly accurate, but also prohibitively expensive for most of the Global South, with prices on the order of tens to hundreds of thousands of dollars per monitor. So you can see here a visualization of just how bad the reference grade monitor coverage is, with one monitor per tens to hundreds of millions of people in most of the Global South, Africa included, versus 1 to 3 monitors per million people in most of the Global North. So this is why low-cost sensors are so potentially impactful for places like Africa. Low-cost gas sensors to measure ambient concentrations of pollutants like ozone or NO2 are super cheap, with prices on the order of tens to hundreds of dollars, super small, and relatively easy to just actually deploy. The problem with these sensors is that they are sensitive to a number of factors. Things like ambient temperature, relative humidity, the age of the sensor itself, and even the exact mixture of pollutants being measured can all reduce the accuracy of low-cost gas sensors. So I'll phrase the problem in this way, that sensor sensitivities make measurements difficult, and that the out-of-the-box data outputs from low-cost sensors really should just flat out not be used. Luckily, we've shown that we can calibrate these low-cost sensors to get high-quality data from them. The question here then becomes what calibration models are the best, and how can we apply machine learning to make better models? I'll just mention that practically all we're doing here is putting a bunch of low-cost sensors next to a reference grade monitor for a time and comparing the results. I won't spend too much time on this. Feel free to pause and examine this or go look at the papers on the last slide. All I'll say here is that so far we've really only examined a handful of machine learning techniques, with neural networks and random forests being the most complex. If you have any suggestions on other techniques we should be looking at, I'd be very interested in talking with you. I also won't spend too much time here, but I will just say that we formalize our comparisons of our models by looking at 3 different metrics. The bias of the model as compared to the reference monitor, the Pearson R as a measure of correlation between the testing data for the model and the reference grade monitor, and the bias corrected coefficient of variation of the mean absolute error, the CVMAE, between the same as a measure of precision of the model. So we'll look at 4 different low-cost gas sensors that we most often deploy: carbon monoxide, ozone, NO, and NO2. Here we can see how our various models perform when we're making individual models for each sensor for carbon monoxide and ozone. Not shown on either of these is the raw data, as it would be way off the scale. But for both CO and ozone, we can see that quadratic regressions are actually fairly good. This isn't super exciting from a machine learning standpoint, but it is good to know that we don't always need lots of computing power for these low-cost sensors. More interesting from a machine learning standpoint is that neural networks do not appear to work well for CO, but they do for ozone. This might be due to the fact that ozone tends to have a cyclic diurnal pattern because of photochemistry, and so an easier pattern is maybe easier for the neural network to pick out, but we're not overall sure. But overall, for these 2 pollutants, our low-cost sensors are doing pretty well. The models that we're making give really high correlations and pretty high accuracy. The story changes a little for our other 2 sensors, NO and NO2. We can see right off the bat that our models for NO give decent correlations, but are very inaccurate, right? Here we're getting some of the best performance out of neural networks, but that's not really saying a whole lot when we're getting coefficient of variations of the mean absolute error of 1, right? We want it to be close to 0. NO2 is slightly better than NO, but still nowhere near as good as CO and ozone. For NO2, we're again seeing that neural networks and random forests perform about as well as the quadratic models. We're not quite sure how to improve these 2 sensors. This could be a data problem in that we don't have long enough collocations. This could be a model parameter selection problem. This could be a model selection problem itself. Maybe there are other machine learning tools we should be using. Or maybe it's just a sensor problem. This is something that we're actively looking into and trying to improve these results here. So I'll end here and just leave you with the following takeaways, right? Low-cost sensors are great for pollution monitoring, but we need to be careful about how we're treating their data. Some of these sensors don't really need smart machine learning techniques, and they respond quite well to these simple regressions. But others of these sensors do seem to be quite responsive. but there's still a bit of work to be done here. Finally, I encourage you to visit the AfriCare website. We're currently in the process of implementing cloud-based machine learning processing for the low-cost gas sensors that we have deployed in various places in Africa. And again, if you have any thoughts, questions, comments, ideas on how to better use machine learning with these low-cost sensors, you can hit me up on Twitter at Africa Quality or shoot me an email. Thank you for your attention.
Thank you. So Mike is not here. So if you have any questions, just send him email. The email is put in the chat box. That's why we are inviting Michael here, because this is actually a very important problem. Those low-cost sensors, maybe somebody say, okay, so the data is not accurate and that's just a junk. No, it's not if we have using machine learning to calibrate them into high quality data, right? So if that is the case, then we're gonna have a whole bunch of data that is available to us to study the Earth science. So low-cost sensors and machine learning, that's a perfect match. So that's a very promising direction that I think I would encourage the community members to look into that. And next, we're gonna go into the first breakout, and Yuhan, moderate.
Yep. Hi, everyone. And so if you look at agenda, that we have go through our first round of lightning presentations. And so we will now move into breakouts. And since we're a little bit over time, so let's shrink it to maybe 12 minutes. And within this first round, that we want each of you to focus on the question that what, so what, and now what. The first what is that what are the factors of success or challenges in these presentations you heard so far? And so what does this mean for the AI and machine learning applications in Earth and space sciences? And what can the ESAP as a community do to help advancing the AI and machine learning applications? And so you can find this Jamboard link in our meeting notes as well. Or and if I'm assuming somebody is already putting this link into the chat. And Annie, could you please just randomly break people into, right now we have 47 people, 10 rooms. So we have 4 to 5 people in each room.
Sure. And a reminder to everyone that after this 12-minute breakout, we're going to have the next set of 3 talks. So don't go too far. Okay, I will create those rooms right now. Hold on. Let's see, we have 40 now. So I'm going to do that. Okay. And open. Welcome back, folks that are coming back in. Welcome, welcome. Hi, everyone. Welcome back. All right. Welcome back, everyone. Okay. Jensen, do you want to introduce our next round of speakers?
Yes. I think we had a very good discussion.
Good.
So next speaker. So I think we all summarized what we have heard in the previous round of talk. AI in earthquake, AI in the snow mapping, the crossphere, and AI in the sensor web or Internet of Things. And the second round, we're gonna focus on some, the architecture, the infrastructure, and maybe the space. So the next speaker is Kevin from Radiant ML Hub. Kevin, are you there?
Yep, I'm here.
Right.
Let me share my screen real quick. Let's see. Okay, can you see that?
Yes.
Okay, great. So yeah, I'm Kevin Booth. I'm a geospatial software engineer over at Radiant Earth Foundation. So we're a nonprofit. We focus on a few separate things. The main thing that I'm primarily working on is Radiant ML Hub, which is our open library for geospatial training data. So we have currently 19 different machine learning training data sets. But let's see, let's get into it. So I kind of stole this slide from my boss, Hamid, and it kind of underscores like the importance of data essentially, and you know, especially in Earth observation machine learning training. Like the biggest issue that you have is just having more and more data to get better and better models. And so in like traditional, computer vision kind of applications, we have ImageNet, which is this giant data set of labeled images that covers a ton of different categories. And they run competitions on it to make sure that the data set's continually improving. And we kind of we don't lack these data sets necessarily in Earth observation, but we definitely need more of them. And so a couple of the ones that we have are Big EarthNet, which is a land cover classification model that was developed, I think, by TU Berlin. Chesapeake Land Cover, which is one that's, I guess, mostly funded by Microsoft. And then also SpaceNet is kind of similar to that in a way. And all of these different data sets, are just kind of key in making sure that we have really good models. And the good thing about these is, at least for Big EarthNet, is it's relatively geographically diverse. So this one, it's situated mostly on European countries, but yeah. And so yeah, that brings me to essentially kind of the problems we have currently in geospatial machine learning is the lack of geodiversity. So if you trained a model just on Big EarthNet, like it would perform really great in Europe, but everywhere else in the world, it might falter a little bit. Let's see, data accessibility, scarce data sources, interoperability. Essentially, it boils down to kind of a data engineering problem on how do we make sure that everything is kind of formatted in a way that's easy for machine learning engineers to ingest it into their pipelines, train a model. So yeah, Radiant ML Hub. So we currently have 19 different catalogs of data sets. We have a bunch of different crop type ones. We also have our own land cover classification data set. This one currently covers Africa and it's Sentinel-2, but we are working with NASA on the Access Cooperative Agreement to expand that to be Sentinel-1. And also our next release is going to be in South America. And then we also host a bunch of different partner data sets. So if you have any machine learning data sets that you'd like to share with us, please do. So a couple of things we're adding to Radiant ML Hub. So we're, I guess we just actually about an hour ago released version 0.1 of our Python library. So this makes it a lot easier to kind of navigate our API and download data sets. And the next thing that I've been working on and I plan on releasing next week is archive collections. And so what I mean by this is currently, the way you access our data, which if any of you have tried this, it's really kind of difficult where each little chip you have to download separately. And that's just kind of an artifact of the way we're cataloging our data sets. But we're going to be compressing them all, like for land cover net, we're going to compress everything over together into one tar file that you can then download and just with one click. So if you're going to be downloading data sets, I'd wait until about next week. We're going to announce that on our social media. And then also part of our Access Cooperative Agreement was we're going to be adding model hosting and model sharing. So we're going to be developing kind of some standards on metadata that represents a model. So, you know, how well it performs geographically, what kind of data it works with. We're still in the user testing phase on this, but part of what we're planning on doing is making it so if you develop a model on one of our data sets, you can host it on there, and then people can easily download that model, run inferences on whatever data set they currently have. So there's still a lot of work there or to be done there, but that's our plan. And I'll end with, these are a bunch of links. So the first one is our registry. This one lists all of our data sets, citations, documentations. Our dashboard is where you can access our API key. So you just create a free account, you'll get an API key, and then our API down there, docs, that'll show you how to, well, it's basically the documentation on how to access our API. And then we have a bunch of notebook tutorials, which we're also updating to work with the Python client, that are basically just kind of, you run these cells and it'll go and download the data. Yeah, if you guys have any questions, let me know.
Great, Kevin. So I do have a question. So it's I know that ML harp data is in S3 basket, right?
Yeah.
Is it directly accessible by the SageMaker?
I don't believe so. We haven't tested that. So our data is on S3. Well, not all of it though. So we use Stack. I think there's another breakout session on this for cataloging our data sets. And what Stack allows us to do is we can link to training data that's on any cloud provider. So we actually, the Microsoft data, that's hosted directly on Microsoft's Azure cloud platform. But the rest of ours are mostly hosted on S3.
Okay. Thank you so much. Great. Okay, so let's move on to the next speaker, Ryan. AI in space weather. Ryan, you get away.
That's right. Let's see if I can get my screen to share here. Is everyone seeing? Let me see if I can go full screen and see if you're seeing the notes or the presenter view. How's that look?
Looks
Perfect.
good.
Great. Thanks so much. Thanks to the conveners for putting this session together. I'm really excited about this. I think it's nice that I'm going towards the end of this session and leading into the next so what, now what exercise, because I've chosen to take kind of a panoramic view. And I'd like to bring a perspective that might be a little bit less normal for the ESIP community. And that's the perspective of the space environment and space weather to talk about some of the trends for AI and ML. And I'm really going to drive to those trends in this short talk. And the purpose is to be provocative, not comprehensive. So what I'd like to do is take a quick tour of AI and ML for the space environment and space weather. And so this is a slide we put together for an AGU town hall we hosted this year from a new cohort of people who are forming a machine learning exploratory committee across the space environment. So that's consistent of a number of these groups across the National Science Foundation, basically communities. And so what this gives you a feel for is just the range of applications and the opportunity in heliophysics for advancing machine learning and allowing machine learning to impact the field as well. So we go from everything from solar-based imagery, where we have a lot of applications for doing segmentation of coronal holes, different active regions on the sun, quiet time regions, coronal mass ejections, trying to use solar imagery with the segmentation approaches to understand what's going on the sun. Then we also get into things like flare forecasting. And it's very important because flares travel between the Earth and the sun in a matter of minutes. And so we really need to forecast them if we're going to be prepared at Earth for how that's going to impact our environment and the space technologies and ground-based technologies that we rely on. And so we have a lot of really sophisticated algorithms that have been developed around flare forecasting. I've posted links to the actual papers that I'm citing here at the bottom if you want to look further. But then we also have instruments sitting in between us and the sun that are in situ taking time series data of what the solar wind looks like. we can couple those with imagery-based data from the sun. So you see a coronagraph image here with a coronal mass ejection erupting off the limb of the sun. And one of the frontiers of machine learning is combining this imagery-based approach with the time series analyses. If we get closer to the Earth, there are also incredibly important applications in the near Earth space environment as well, such as predicting the radiation environment that we see. So how do we understand the radiation that's going to affect our technologies and in the future, our astronauts that are in near Earth and even cislunar space? So predicting the radiation environment is another big application. One of the main things we want to try and do there is take single point measurements of this vast magnetospheric region and actually reconstruct a global three-dimensional time-dependent picture. And it's some fantastic work that has been done there. One of the indicators that we use to kind of wrap all this information into single numbers are geomagnetic activity indices. So this is really how the space community talks to the ground-based community through these indices. So we try to develop, and one of the things that goes back for decades is developing algorithms that predict these geomagnetic activity indices. Work that I've been heavily involved in is actually focused on this interface between the ground and space. So how does the space environment affect all of the things that we look at on the ground, such as radio waves, radio signals that are passing between us and satellites. So those are severely affected by space weather, and they're actually a really potent data source, time series data source to apply machine learning aspects to. We've done a lot of that for predicting how those signals would be disrupted with different machine learning algorithms, and I've cited a few papers for you to look at down there. But what I really want to do is highlight the trends that I think this emerges here, and what I think it means for this group that is convened today. So I'd like to use this tour through the applications to emerge some of what I think are the non-obvious trends, some of the things that are perhaps less well talked about. And so I hope that this will help emerge some of the conversations that are not being had as much. So again, we're trying to be provocative and not comprehensive here. So the first trend that I kind of think about a lot is this concept of AI readiness. I think that this concept has been part of the community discussion for a while, but it's really been couched in the concept of AI readiness for a data set. And I'd like to raise the question of how do we make a community AI ready? I think that's obviously a challenge for a number of reasons. One, because there's sprawling definitions of what AI and ML actually are. Those boundaries between AI and ML and other approaches aren't necessarily very clear. I also think a challenge is the hype of the AI and ML algorithms. A lot of people who may not have a great understanding of them think that they're this magic wand. You have a problem and you just throw AI and ML at it. And that can actually be pretty damaging for a community to be AI ready, to kind of stay back from that understanding that's needed and expect it to solve the problem. And I think that's also part of the other challenge where there's different levels of understanding and readiness to adopt AI and ML. So there's a few things I think it implies that we should be doing. I think really we need to be immersing ourselves more in the AI and ML research community and really understand that it actually is a research community in and of itself to develop these new algorithms and bring them into ours. I think there's a couple of excellent examples of that. The NASA Frontier Development Lab, which I've been involved with for several years. And then more recently, the NOAA workshop on leveraging AI for the environmental sciences. I think that both of those communities have been doing a really nice job of that. I think it also means we need to be doing better jobs of developing tools for collaborating. And I think this kind of drives to us being able to package our research objects with data and model workflows. So I know there's some great examples you've seen this week about using Jupyter notebooks for that. I think that's a really great way to go forward. The second trend that I see and work on is through knowledge graphs. I think rather than seeing these as a nice to have, I think we need to see these as a must have for robust AI and ML. We have to develop better relationships and better utility for bringing different data sets together. And I think knowledge graphs allow us to integrate these diverse data sets. This is the challenge that's really punched home in the heliophysics environment. And I think with many of these studies, it's clear that we're actually using a woefully small amount of available data and actually the small amount of the available knowledge. One of the challenges of that is just very difficult to integrate knowledge. And so knowledge graphs has been a tool for us to do that. What does it mean for what we need to be doing? I'm sorry. I think we need to be linking data. We've talked about that a lot this week. I think there's some excellent resources, but I think it needs to be brought into the AI and ML conversation as well. So the third trend that I want to talk about is computability. And I've listed these things here for your reference, but I want to talk just a little bit about what I mean by that. I think this is very important. I think it means that we have a detailed knowledge at the finest scales in the systems that we're studying, but we don't always know what the right level is to look at them. And I think all of the AI and ML approaches that we take have to make a coarse-grained assumption in some way or another. We all want to incorporate the physics that we have into our models, but physics-based models are very expensive to run. And so that's another challenge in bringing that in. And then as we run those, we generate huge volumes of data that can be prohibitive to our approaches. And so what we need to be doing is speeding up the use and generation of these physical models without losing fidelity. And so there's this trend of using emulators to model with AI and ML these physical models. I think we need to become more practiced in high performance systems, high performance computing systems. And one of the lessons from that is to move the compute to the data and not the other way around. So becoming more familiar with how we actually achieve that. And the final trend that I want to highlight today is really in understanding the models that we produce. We need more robust evaluation of those models to actually understand what it's telling us, what it's capable of, and more importantly, what it's not capable of. I think it's easy, and anyone who's reviewed or looks at the machine learning literature for the Earth and space sciences recognizes there's kind of a standard form. We find some data, usually a small subset of it, train a model from out-of-the-box settings, and there's kind of insufficient optimization. Then we gauge the performance of that model against some coarse parameter like mean squared error. And so I think that approach has currently been considered publishable, but I think it's really minimal, and I think we can go a lot further and need to go a lot further with AI and ML. And so I think fully understanding that those kind of models that we're developing is very challenging. And then finally, the challenge is it's very difficult to know precisely what the model is actually optimizing for. The lesson is that we're always going to overfit to something, whether it's a specific narrow application or a metric. So it's important to know what you're optimizing for. So what do we need to be doing? I think we need to better qualify what we're optimizing for, recognize the limits of the generalizability of our model, and somehow capture that in the delivery of these models. I think we need to expand what we're evaluating our models over. I'm actually listing a paper here where we outline 3 different levels of evaluation that our machine learning model was put through as a framework for future models. So you can get that archive paper at your leisure. And then I think one of the really important and exciting things is loss function engineering. Francois Chollet, who I consider a thought leader in this field, argues that one of the single most important advances for AI and ML is engineering the loss function to more precisely optimize what we're looking at. And then finally, I just want to introduce this concept of socializing the evaluation of AI and ML models. What if you created a model, put it out there for anyone to pick up and evaluate in the way that they would look at it, so we get a more robust understanding of it. So just to close, I wanted to put up the trends and the actions that I see. And then I put together a few kind of wide-ranging resources that I really love that you may not be aware of yet, but I think can be valuable to you. So thanks again. I'd love to interact further.
Thank you so much, Ryan. If you can set us these slides, I would like to include them into the repository of the ESIP.
Absolutely.
Mm-hmm. So I think we are running low on the time. So Ryan, if you go to the Slack channel, you can respond to the question there. So last speaker is me. Okay, so I'm gonna summarize the efforts of the ESIP machine learning cluster in the past year. I'm gonna share my slides. Okay, so this is what I want to talk about. So what we are planning to do as a community in the next year. I would say we should work on the Earth AI. We will formulate some efforts needed by the ESIP cluster community and get something done. So I'm Zhen Sun from George Mason University. I'm currently the chair of the machine learning cluster, and we have a Slack channel, machine learning mailing list, and a wiki page. And feel free to join us, and you're always welcome. So first, introduction to the cluster, to this cluster, and we are funded by Ann Wilson. I think maybe 2 or 3 years ago. And the original purpose is to educate ourselves about the machine learning through sharing all these knowledge, experiences, and resources, and answering questions. But that was the original purpose. Things has changed a lot in the past 2 years because technique developed very fast. So this is a new goal of the cluster right now. And we want to bring together community experiences, catalyzing machine learning research in geosciences, and move forward to the vision of Earth AI. Probably you will ask, what is Earth AI, right? Because you heard a lot of AI terms like Geo AI, the health AI, and probably the space AI, weather AI. But what is Earth AI on Earth? In my opinion, or we think that Earth AI is a very huge system that will enable the disaster control, weather control, and agriculture automation. What is disaster control? We will have the ability to predict, to control all kinds of nature hazard, maybe the space hazard, like from the space weather or from earthquakes, from the hurricanes. So all these disasters can be under control by the AI. And AI will know when it will happen and how to avoid it. And weather control is like, if we want to get a snow, we will get a snow. And that kind of thing can be realized by AI in someday. And agriculture automation, of course, we are doing all the precision agriculture right now. And in someday, AI can help us to achieve the biggest yield without the intervention of human labor or something. So that is the Earth AI vision. And if you want to know more details about this vision, you can read those Galactic Empire novels by the Isaac Asimov. He wrote these books. I read all of them, 12 of them. And that's very impressive. I think that is what Earth AI should look like. And currently what we should do, right? So there is billions of dollars are pouring in this AI market, and we are not going to sit there and waiting things to happen. We are gonna do something. So I was thinking about what we should do, what we can do with our, the available resources to us. And there is at least two things we can do. The first thing is we're gonna build a GitHub repository, and that is called Awesome Earth Artificial Intelligence. That is Awesome Earth AI. And this is our long-term, actually it's gonna be maintained for a very long time. And we're gonna updating the list, and everybody can look for resources, and there's their starting point. If they want to get involved with the AI work, they can start from there. Another thing that we can do is a review paper about the current status, where we are about the AI in Earth system science, and where we should go. So that is short term. We plan to finish this paper or maybe this book, because somebody are arguing me to telling me that there is too many papers and we should, it's too much work. And it's too much work to put in one review paper. So probably we can write a book or something. But I expect that this work can be done in this year. So that is our short-term goal. And these two efforts, everybody is welcome. So if you want to get involved, just join us and send us a message, and you're welcome. So everybody is welcome. Everybody is invited. And the door is always open. So feel free to join. And what is the Awesome Earth AI repository? So first, when this idea came up in my mind, because I found that almost every AI engineers, they are staying on GitHub. They spend a lot of hours on GitHub and they search everything there. And Awesome List is one of the major information sources for them. And why not we are starting an Awesome Earth AI list, right? No, there is no other this kind of awesome list before. I searched that there is no one else doing this. So we should start this one by ourselves. We initiated this one, and the repository is under the EC-Fed organization, and you can check the GitHub and you can find this repository. So what is awesome? What's the definition of this awesome? The first, it has to be open source license, like MIT Apache 2.0. So all these licenses are a very good license. You can use it without concern or without worries about, someday people will charge you money or something like that. And about the projects should be easy to get involved with, like all those projects that people can contribute something into it. That is awesome, right? And about dataset are awesome if they are fair. And publications that can make it easier to navigate and obtain the information and software. First, it has to be beautifully documented. People can easily learn how to use the software, and it's very easy to install. Maybe only one command line would be enough. That is awesome. And it has to have great examples and tutorials, API, and fully tested. So this is awesome. And we only include those resources that maybe met one or two criteria of this list. And besides the existing resources, we also included some machine learning enthusiastic scientific questions, like for the geosphere, how do you identify hidden signals of earthquakes, which covered by the Mustafa. And I will put the Mustafa's paper and the data set here. So somebody else, if they are starting earthquake and they want to, use machine learning, they can go to this repository and find the Mustafa's work and then get delighted and maybe decide your work and use your data set. So that's a very good starting point. So that's the point of this repository. And I would encourage everybody to contribute to this table. That would be awesome. And about the review paper, we have, actually it's a community effort. We have identified 10, actually I missed one. I forgot which one I missed. There is 10 urgent challenges to work on. The first one is model selection. There is maybe hundreds of models published last year in the Neuro IPS, in all the computer science conferences. Every paper is a new model. There is 1,000 papers. There are 1,000 models. Which model is best fit for your problem? Nobody knows, right? Model selection is a very critical challenge right now. And the training data set preparation, I guess everybody knows this. Optimization, actually machine learning itself, it's in nature, it's a model, it's a optimization problem because machine learning doesn't understand anything about except the 1 and 0, the numbers. So optimization is its only goal to learn something. And we need to make this thing work better because right now there is a lot of limitations of the machine learning model. And the parallel computing, because right now the machine learning model is just a regression, so we have to make it work for big data. Big data is the precondition for the model to be operational. And also the expandable AI. So machine learning is actually no longer a black box. And the spatial temporal generalization, if you train a model, you want to use it in another area, how to make it work? Uncertainties, every time you train a model, the results is different. So that's a big problem actually. And integration with physical models. So we are not going to dump all the existing conventional numerical model. We are gonna integrate with them, or we want to use a machine learning model to reduce the computational cost and improve their accuracy. So how to integration with the existing models is a big challenge. And also AI is non-transparent right now. So we want provenance to make it transparent. Yeah, so that's basically the two efforts we are working on right now. And we have a monthly call on every third Friday, 12 p.m. to 1 p.m. Eastern time. And we have mailing address and a Slack. Everything is here, and I'm gonna put these slides to somewhere that everybody can get access to. Okay, so yeah, think about how to make teach the AI to tell a joke. That is actually very interesting because AI actually right now is far from the real AI. We are still at the first stage. And maybe the models you train today will be, will be forgotten. It's no longer be useful in 1 year or 2 years. So think about the evolution, think about the progress, think about the ultimate goal of the AI. That's our ML clusters ultimate, topic about this thing. So let's just move forward together and working on AI together. I think that's it. Thank you.
Great work as always, Jensen. We do have a couple minutes. I think we could just take some questions now or open up the discussion instead of going back out to a breakout and just see. There's been a lot of comments in chat. Most people have been answering the questions that have been coming up, but I wonder if anyone has any questions they'd like to ask Jensen about his presentation, or any thoughts about those initiatives that he mentioned relative to the ESIP machine learning cluster. So feel free to raise your hand in the participants list if you would like. We've got a couple hands that went up. Let's see, Jackie, do you want to unmute and ask?
Hi, thanks. That was a really nice talk, and I love to see the community building going on. So I'm a bit new to the machine learning and AI side of things, but looking at some of the data I've been working with, I've been really interested in unsupervised learning because with the data that I'm working with, actually obtaining labeled data or assigning labels almost feels somewhat arbitrary. And I'd really like the data to tell me instead of me assigning things to it. Do the experts in the room have any thoughts about using some of these unsupervised tools?
Yes, I think that's a very common challenge actually. So first we need let the data speak by itself. Unsupervised classification is actually a very mature technique, but sometimes it's very tricky to use. Like the k-means, you have to specify k. So you have to know how many clusters are there, I think the unsupervised learning, the key problem is hyperparameter tuning. So it still needs some training process, just like the supervised learning. But the tool like the Python or scikit-learn, those libraries provide a very useful modules that you can use. The entry of Barry is very low. So I think you can try that on the Python scikit-learn. I will put it in the chat box.
I was going to say, Jensen, do you want to put those resources in chat?
Yeah.
Yeah, and I was just wondering about some more complicated things such as like self-organizing maps, moving beyond like a k-means type algorithm and actually leveraging neural nets. But that's a specific one. So
neural network can be used for, I don't think it can be used for unsupervised learning. Maybe I don't know about that. Anybody know about using neural network on unsupervised?
There is some work using the GAN to generate some samples that it's part unsupervised and then can feed into a supervised model later on. So a lot of work has been happening, like you said, self-organized maps, Jackie, and the other things for anomaly detection a lot that has been used in different models. And I will just stop here and we can chat in the Slack or just email to the ESIP cluster, machine learning cluster email list. And I'm sure there will be a lot of conversation going on with that.
Mustafa, do you have a comment for Jackie?
Yes, I just want to add to that, like GAN might be good, but it's kind of controversial. Like people don't put GAN in a like traditional unsupervised technique, although it can be one of the unsupervised. I want to just add that in my talk, one of the methods that I pointed out was using deep neural network for unsupervised clustering of techniques. So these are relatively new techniques that are getting popular to use basically deep neural network to extract the features that are most useful for a particular clustering task, unsupervised, like grouping of the events. And they generally works by optimizing simultaneously two loss functions. One is for extracting the feature, automatic feature extraction, and the second one is to optimize the clustering loss. So that's the big groups of techniques. We had one example of such in one of the advantage of these techniques are actually not only they don't need any label, they also work fairly well on relatively small size data sets. So you can get a pretty good performance similar to a large scale supervised learning using these deep unsupervised deep learning techniques.
Yeah, compared to unsupervised learning, I think it's more realistic to do a learning on small scale data, small scale training data set. As I put in the chat box, there is a work using very small scale training data set to get a very good performance on very large testing data set. I think that's probably more realistic than unsupervised learning. What do you think, Jack?
Oh. Yeah, so thank you all for your input. That was extremely helpful. Yeah, so you're then also recommending just training. I've seen some papers showing the small training set and that can be successful. And Mustafa, I'm gonna have to go back and revisit your presentation to see if I can find some more details.
Yeah, I just add the link and title of that paper in the chat.
Awesome, thank you.
All right, so we are at the end of our session, but Tom, you had your hand raised. Do you have one quick question that you wanted to put out there before we all say goodbye?
I wanted to come back to Ryan's point about knowledge graphs and how they might work with machine learning and these various AI techniques. And I was just kind of wanted to open it up to the community about, I know ESIP has active clusters and committees in both areas, and was curious of what that interaction might look like and how we could get the two groups at ESIP communicating on that topic.
Ryan, it looks like had to bounce off, but I think that it's a good way to end because a lot of what we've talked about this year within ESIP is cross-cluster coordination. And so I think for Yuhan and Cindy and Jensen to hear that as we look for those synergies between clusters, that even between the knowledge graph folks and the machine learning, that's another connection that could be made and another conversation to have. And maybe Ryan could restate that call and help facilitate that conversation. So I think that's a great, maybe not time for discussion now, but something I'm looking at you, Jensen and Cindy, that to bring up in your next cluster meeting. So So with that, I'm going to say thank you to everyone. This has been a really fantastic session. We do have a coffee break coming up that I would really recommend everyone stopping by. You can keep this conversation going if you'd like, but just head back to Kiko Chat and look for coffee break on the left. We'd love to see you all there. And I think you noted about resources, but generally what we do after the ESIP meeting is everything is linked through Sched. So speaker presentations, the recording, and all of these resources. So that's kind of our place to find things after the meeting. So that 2021 ESIP winter meeting.sched.com will have all the links to presentations, and we can add some of these additional resources there that we can pull out of chat. So thanks everyone, and we'll see you at the coffee break.